Alright guys, this is your video on the normal force. Sounds like a weird word, but it actually makes a lot of sense when you think about it. So here's an object resting on a level surface, and the normal force is very important for any object that rests on a level surface. Basically what the normal force is, and you want to just define it here. It's a support force. Alright, so the support doesn't always have to be where an object is supporting something vertically, like when an object sits on a table, but it could be, even in a roller coaster loop, whatever. Any kind of like push from a surface is a normal force. Alright, so let's draw a force diagram of an object just at rest on a level surface. You can see that's written right there. Well, we know gravity, because it's on Earth. Anytime you're on Earth or some planet, you've got gravity pulling you down. So we're going to FG down. You notice we're starting to draw forces now in the Y direction. I'm going to break out the axes right over here real quick. There is on our world an X and a Y axis on everything. We were using Newton's second law previously in the X direction. And now we're going to start to apply it to the Y, and eventually we'll do both at the same time. Alright, so gravity pulls something down that's sitting on a surface, but if that was the only force on an object that's sitting on a table, what would that object do? Well, right now gravity is unbalanced. So if that was the only force on an object which sits on a table, then the object would accelerate down. It would go straight through that table. So what we know from our eyes is that in order for that object to remain at rest on the table, there needs to be some balance to gravity, some force balancing it, and that force is called the normal force, Fn. Right next to the definition of normal force, we write Fn to represent it. So if gravity, these are balanced. Why? Because in order for an object that's sitting on a level surface to remain at rest, the net force in the Y direction, when you add up normal and Fg is down, so minus Fg, you better get 0 for it to remain at rest. So the normal force, you could even bring it down. What if you added Fg to both sides here? We know normal force is basically going to be equal to gravity, because they're balanced. That's what balance means. They're equal, they're the same. Now, this is true for an object at rest on a level surface. It remains at rest. Normal force and gravity are balanced. But it's not really true in every situation. If you're on an elevator and you hold this package or put it on the floor on the elevator, and the elevator accelerates up, normal force would be greater than gravity. Or if the elevator accelerates down, gravity would be greater than normal force. But that's not the situation we're dealing with yet. But we will get there. For now, since AY basically is 0. That's why the forces are balanced. They have to sum to a net of 0. Okay. So let's just do a problem where we calculate the normal force given the mass of a box. So we're going to use Newton's second law, but previously we had applied it to the X direction, horizontally. Now we're going to apply it to the Y direction. You need to be able to apply it to both directions. So use Newton's second law applied to the Y or vertical direction. Well, remember, whenever we use Newton's second law, we always draw a force diagram first. So if something is simply at rest on a table, same force diagram as before, last page. It's on Earth, so gravity pulls it down. table supports it with a normal force. Nobody's pulling to the left or to the right, so we don't have to draw those yet. We don't have to add the horizontal yet, but we'll get there. There's no friction because it's not sliding really, and friction isn't like preventing it from being budged or anything like that. So let's calculate FG. We know the formula for FG, and we're going to have to calculate FG first before we get the normal force, all the time. Equals the mass of the box times we're on Earth. So the weight is mass times 9.8. It's 4 times 9.8. Take out your calculators. 39.2 newtons. So that's the weight. That's the weight, but how much is the normal force? Well, you might just go right ahead and say, hey, I know they're balanced if it's at rest. But if you're on an elevator, it's going to be wrong. So what you have to do is use Newton's second law now. It's the up force minus the down force when we apply the second law to the y direction. Right? So really what you were doing before was you were saying F net x. You were using Newton's second law in the x direction, all right? And we will, we're not going to do that right now, but we'll combine the two later. But now we're going to apply Newton's second law to the y direction. Instead of right minus left, it's up minus down. And when something remains at rest and it's not on an elevator, AY is 0. So we could say M times 0 is 0. And plug in your FG. And you can see just visually here, what's Fn going to be? 39.2. So just like before, using Newton's second law applied to the y direction now, you always need the force diagram first. If it remains at rest, you know AY is 0. You could plug that in and then go ahead and calculate weight, and that'll get you your normal force, knowing that AY is 0. Thanks, guys.